Hi everyone, I'm Dan Fullerton, and today I want to talk to you about electric fields due to charge distributions. Our goals today are going to be to calculate the electric field of the center of a circular arc of charge, the electric field due to a thin straight insulating wire, the electric field on the axis of a thin ring of charge, and the electric field due to a thin disk of charge. Now, because this could get pretty lengthy, I think we're going to break this up into two separate videos. The first one will cover the circular arc and the uniformly charged wire, and then the next two will cover the thin ring of charge and that uniformly charged disk. So with that, let's dive in. The electric field due to a thin semicircle of charge. A thin insulating semicircle of total charge Q with radius r is centered around point C. Determine the electric field at C due to the semicircle of charge. Well, the first thing I'm going to notice here is that I have a symmetry about point C. Horizontally, I've got the same thing on both sides, and since it's uniformly charged, I can state that there's not going to be any net horizontal electric field. It's going to cancel out. So all I really have to worry about is the vertical component because of that symmetry. That'll help. My general strategy, though, is going to be to take little tiny bits of charge and find the electric field due to each of those, and then sum all those up with an integral. So to start that, I'm going to pick a little tiny piece of our semicircle that has some charge dq, and I'm going to define that in terms of its angle. If I call that angle theta, then this angle will be d theta. And if the radius is r, then the length of this little tiny differential of that semicircle will be r d theta, holding charge dq. Finally, let's define a linear charge density here. The linear charge density for that arc, since it's uniform, is going to be the charge divided by the length. Or in this case, our total charge is q, and our length, well, once around a circle is 2 pi r, so a semicircle must be pi r. And with that, let's get started. Let's figure out the electric field due to just this little bit of charge, that little bit of the semicircle. So the differential of the y component of the electric field is going to be 1 over 4 pi epsilon naught, the permittivity of free space, times our charge dq over our distance from that charge squared, r squared. And since we're just looking for the y component, that'll be times the sine of theta. Now that dq we already defined. The little charge in here must be the linear charge density times the length of that line. So we can say, since dq equals lambda r d theta, that the differential of ey equals 1 over 4 pi epsilon naught lambda r d theta over r squared sine theta. And right away, there's a couple simplifications we can make. I see an r versus an r squared there. Lambda is a constant. We'll get that over here. And r is also a constant. So if I integrate both sides, on the left-hand side, I'll have the integral of the differential of the electric field, the y component, must equal, well, let's pull out our constants, lambda over 4 pi epsilon 0 r integral of sine theta d theta. In our limits of integration, if we're going from theta, we're going from theta equals 0 to theta equals pi. So our limits are from 0 to pi in radians for theta. All right, the left-hand side, the integral of the differential of ey is just going to be ey. And the right-hand side is going to be lambda over 4 pi epsilon naught r. The integral of the sine of theta is the opposite of the cosine of theta, and that's going to be evaluated from 0 to pi. So that implies then that the electric field due to y, in the y direction, is going to be lambda over 4 pi epsilon naught r negative cosine of pi So that'll be minus cosine pi minus negative cos of 0. Minus cos pi, negative 1, that's going to be 1, plus 1. So I'm going to come up with 2 lambda over 4 pi epsilon naught times r. Or 2 over 4, that's just 1/2. So the y component of the electric field must be lambda over 2 pi epsilon naught r. So we get into some pretty heavy math, but really all the work is in the setup. Taking that little tiny bit of charge, finding the electric field due to that bit of charge, and then integrating, adding up all those little bits to give us the whole. There's our general strategy. Now the next one, we're going to do a thin straight insulating wire. This one's going to get a little bit more involved. The electric field due to a thin straight insulating wire. Find the electric field some distance d at point P from a long straight insulating rod of length L. We'll assume that it is uniformly charged, and this has to be perpendicular, the line from the center of that wire. We could do it at any point, but let's keep things as simple as we can, because this already is going to be a bit more involved than the last one. Our general strategy again is we're going to divide the total charge Q up into smaller charges delta Q and find the electric field due to each little delta Q. Then we find up the total electric field by adding all of those up, and we can also make a symmetry argument here. Because we have this symmetry, it should be pretty straightforward to say that we really only have to worry about the horizontal component. The y component should cancel out because that's uniformly charged and we're in the center of the wire. So to do this, if our whole wire here is length L, then let's call this L over 2. This end will be minus L over 2. Let's also define, let's take a little bit of the wire here for our dq or our delta q. We'll define the distance from our axis as y sub I to that little bit. And we'll also draw a line from our little bit of charge to our point, realizing that our electric field then must be something like this. There's our little bit of electric field due to that differential little tiny piece I. Our radius to that little piece, the distance, is Ri, and this then must be theta I. And once again, we'll talk about a linear charge density. Lambda equals total charge Q divided by total length L. I think that'll get us set up for starters at least. So we're looking for the x component. So the electric field to that little piece I in the x direction is just going to be the total electric field EI times the cosine of theta I. Or, in this case, that will be 1 over 4 pi epsilon naught times our little bit of charge, delta Q, over Ri squared, our distance, times the cosine of theta I. Now we've got to do a little bit of math here. First thing we can recognize here is Ri is the hypotenuse of a right triangle, where Ri is going to be equal to the square root of yi squared plus d squared. And by that same token then, cosine of theta I, well, cosine is adjacent over hypotenuse, so that's going to be d over Ri, or d over the square root of yi squared plus d squared. So I'm going to substitute in for cosine theta I, d over square root yi squared plus d squared, and for my Ri squared, I'm going to substitute in yi squared plus d squared. So this then implies that EI in the x direction is going to be 1 over 4 pi epsilon naught delta Q over Ri squared, which is yi squared plus d squared, times our cosine theta I d over the square root of yi squared plus d squared. Or if I put all this together, that's 1 over 4 pi epsilon naught d delta q divided by yi squared plus d squared. Square root times the full thing will be to the 3/2. Now my next step. What is this delta q? Well, delta q must be q over L times our little bit of dy. So this implies then, since delta q equals q over L dy, that EIX must be equal to 1 over 4 pi epsilon naught dq dy over L times the quantity yi squared plus d squared to the 3/2. Or let's integrate that now. The integral of the left-hand side, the integral of EIX, is just going to be the total electric field, EX. And the right-hand side, if I integrate this from minus L over 2 to L over 2, I can pull a lot of these constants out. D and Q are constants. 1 over 4 pi epsilon naught is a constant, and L is a constant. So I can write this as dq divided by L over 4 pi epsilon naught integral from y equals minus L over 2 to L over 2 of dy over y squared plus d squared to the 3/2. Now, to take this next step, really have to go looking up in a table of integrals in order to integrate this. I don't know this one off the top of my head, but I can go to the back of a calculus book and figure it out. So let's give ourselves a little bit more room here as we move forward. And the way I'm going to justify this is using the formula that I know that says that, back of a calculus book, the integral of something of the form dx over a squared plus x squared to the 3/2 is equal to x over a squared square root of a squared plus x squared plus c. If you know that off the top of your head, more power to you. I've got to look that one up. So I'm going to use that because my integral here fits that form. So EX then must be equal to, we've still got our constants, d times q divided by L over 4 pi epsilon 0. Now we've got our x over a squared, square root a squared plus x squared, but we use our variables here, so that's going to be multiplied by y over d squared times y squared plus d squared to the 1/2, the square root of that, all evaluated from minus L over 2 to L over 2. All right, a little bit more algebra now. Let's make that, well, we've got a d squared here and a d up there, so we're going to end up with something of the form q over L divided by 4 pi epsilon naught d times the quantity L divided by 2 divided by, well, we've got L over 2 squared plus d squared, all raised to the 1/2, minus L over 2 over minus L over 2 squared plus d squared, all raised to the 1/2. And with a little bit more algebra, I can show then that that's going to be equal to q over L divided by 4 pi epsilon naught d times L divided by L over 2 squared plus d squared to the 1/2. Or trying to put this all together, we've got Q over L times L. That's just going to leave me Q in the numerator. So the electric field in the x direction is going to be Q divided by 4 pi epsilon naught d times the square root of L over 2 squared plus d squared. Whew. That's a lot of work, but there it is. So that's for a finite straight insulating wire. Well, the question you might ask yourself then is, what would happen if that was an infinite rod? If that rod kept going and going and going? Well, let's take a look and see. In that case, the electric field in the x direction would be equal to the limit as L approaches infinity of what we have over here, which you've got to be careful, because notice that Q, because we have a constant linear charge density, Q is going to go up towards infinity as L approaches infinity. So we can write this as the limit as L approaches infinity of Q over 4 pi epsilon naught d square root of L over 2 squared plus d squared. As L goes to infinity, Q goes to infinity too. But here in the radical, square root of L squared plus d squared, well, L over 2 squared, that d squared is going to quickly become insignificant. So we're going to get over here, we're going to get just an L coming out. That's going to be the important part, as that goes to infinity. So that's going to be equal to Q over 4 pi, oops, let me rephrase, that's going to be equal to the limit as L approaches infinity of Q over 4 pi epsilon naught times d times the quantity L over 2. When we do that, well, 4 divided by 2 is just going to be 2, so Q over 2 pi epsilon naught dl. But remember, lambda equals Q over L, so that just becomes Ex equal to lambda over 2 pi epsilon naught d. What if the distance d is infinite? Well, let's take a look and see what happens in this case. Give ourselves a little bit more room here. If d is infinite, well, Ex is again going to be the limit, in this case, as d approaches infinity, of Q over 4 pi epsilon naught d square root L over 2 squared plus d squared. And pretty easy to see as this happens, that's just going to go to Q over 4 pi epsilon naught d squared. That L becomes insignificant. So it acts like the electric field of a point charge as you get further and further and further away from it. Q over 4 pi epsilon naught r squared, if you recall. All right, I think that's enough for this one. We'll come back with a couple other charge distributions here in our next video. Thanks for your time, and if you need more help, check out aplusphysics.com. Make it a great day.